Hi everyone. Today we are going to find the electric field along the axis of a uniform line charge. Okay, in order to solve this problem, let's firstly draw this. We are going to draw a line charge. This is the line charge. This is a green colored line is the line charge. Let's say that this line charge has length of L and it has a charge density denoted by rho sub L. Okay, now due to, as we said, we want to find the electric field due to this line charge along the axis. I attached this line along the z-axis, and the point and the arbitrary point where we want to find the electric field due to this line charge will be on this z-axis. This is the point P, and it has the coordinates of 0, 0, z. The approach that we will pursue to find the electric field due to this line charge is applying the gradient operator upon the potential. So we want firstly to find the potential. We know the equation for the potential due to an arbitrary point in the free space. It's represented by this, where Q is the total charge of this line charge, and R is the distance between this line and the point where we want to find the electric potential at. After finding this, we will apply the gradient operator. We know that the electric field is the negative gradient of the potential. This form of this equation is optimal. We want to find the electric potential due to a discrete points. But in this case, this line charge is continuously charged. So we are going to find another approach. I will take a small piece from this line charge. I will call it by dz. And in order to avoid the ambiguity between the coordinates for this point and for the line charge, I will make the coordinates of the line charge to be primed. Now we want to find the electric potential due to this small piece of line charge, which is dz. The charge due to this point, due to this small differential line is equal to the length of this line times the charge density. And in order to find the distance between this differential line and this point, let's first determine the origin. Okay, this is the origin. Let's make the origin to be at the middle of this line charge. Okay, this is the origin, and accordingly this line charge is going to be split into two equal pieces. Each of them has the length of L over 2. Okay, let's say that the distance between this line charge and the origin is z primed. Okay, this is z primed, and the distance between this point and this charge is z, according to the coordinates that we determined before. So the distance between the point and the differential line is z minus z primed. Okay, so R is equal to z minus z primed. Okay, now let's plug these two, the right hand sides of these two equations inside this equation, and we will have, and this is the potential due to this small differential line. In order to find the potential due to this whole line, we want to take the integral with respect to this differential line, this small differential line, which is dz primed, and the ranges are going to be between minus L over 2, okay, and L over 2. Okay, now let's apply the integration. But before applying this, we are going to take all constants out of the integration. Now the integration of this is equal to the ln, or the natural logarithm of the denominator z minus z primed. Now let's substitute the limits for, now let's substitute these limits for z primed, and we will have, and this equation is only valid when z is greater than L over 2, or by other words, when the point exists up to the line chart. In order to find the electric potential down this line charge along minus z axis, we are going to do the same operation, but anyways, we are not going to dive into this. Now, from this equation, we are going to find the electric field by applying the gradient operator. We all know that the gradient operator is the partial derivatives along the three coordinate systems, and as we see, this equation is only function of z, so the derivatives with respect to xy in case of Cartesian coordinate systems, or r and the azimuthal angle in case of the cylindrical coordinate systems are 0. So we are going only to take the derivative with respect to z. So, and this whole part is constant. So we are going to take it out of the derivative. Now the derivative of the ln, now the derivative of the natural logarithm is equal to the derivative of what is inside this natural logarithm divided by what is inside this natural logarithm in the first place. So it's equal to, now in the numerator we are going to take the derivative what is inside this ln, and this is the equation, and this is the derivative of the fraction. How to find the derivative of the fraction? We're going to find the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator divided by the denominator squared. Okay, according to this we will have, and the power of this is going to be eliminated with this. Okay, and the product between both of the and the product between these will yield the difference between the square of these two terms, which will yield z squared minus L over 2 squared. Okay, and the minus sign is going to be eliminated, so the final answer is, and this is the final equation, the electric field at the axis of line charge.